Hey guys, what's up? My name is Atharva Tyagi, and I'm going to be explaining to you the lifespan of a tornado. So first, I'm going to read out what's going to happen when this tornado is forming, and then we're going to break it down on the whiteboard. So all tornadoes are going to come from a thunderstorm. Firstly, a supercell needs to develop from an unstable atmosphere. This supercell is going to split into a right mover and a left mover, and in the northern hemisphere, the right mover will continue to strengthen because it'll be rotating cyclonically. It will develop a strong updraft, a well-defined rear flank downdraft and front flank downdraft, and the hook echo will become clear on radar. The supercell will have a cyclonically, which is counterclockwise in the northern hemisphere, rotating mesocyclone, which is the rotating updraft caused by wind shear. And this is all according to metoffice.gov.uk and Orf et al. Alright, so I have this diagram that I've tried to mock up, and it comes from this image. It's quite difficult to see, but the source is going to be Graph Michael Supercell Side View from Wikimedia Commons, created on July 26, 2005, and the license is Creative Commons by 3.0. So what a supercell is, so first of all, the importance of tornadoes is that tornadoes most often form from supercells, but what a supercell is, what sets it apart from other thunderstorms is that the updraft is rotating. So let's set out two things first. All thunderstorms are going to have an updraft and a downdraft. Updraft is warm air that's going to be feeding off of, and the downdraft is that once that warm air gets up, it cools down, it's going to come back down. So this squiggly thing is the rotating updraft, which is called the mesocyclone. So the reason it's rotating is due to something called wind shear. So wind shear is changed with wind direction or wind speed as you go up in the atmosphere. So I'm going to give you a hypothetical situation right here. So at the surface, we got winds out of the southeast. All right, out of the southeast, and they're at 5 knots. 5 knots is maybe like 6 or 7 miles an hour. And as soon as we get up to 1 kilometer in the atmosphere, say like around here, 1 kilometer. I just want to make sure you know this. The diagram is not to scale at all, but as we get to 1 kilometer, we're going to have the winds coming out of the southwest instead. And the winds are going to be at least maybe, let's say, 35 knots out of the southwest. Now we get up to 3 kilometers, and the winds are, let's say, 55 out of the west-southwest. We get to 6 kilometers, we say they're 80 out of the west. So we get all the way to the upper levels, maybe around 12 kilometers. It's 100 out of the west too. So that if you notice, if you were to look at how the directions are going, southeast is this way, southwest is this way, west is this way. So we have this sort of rotating this not counterclockwise, but still we have this rotation setting up. And additionally, the wind speeds are also changing. So this causes the updraft of a thunderstorm to tilt and start rotating. So this is basically a rotating column of air, the mesocyclone. So now that we've set that in, as the winds go upward, we're going to have the downdrafts coming down. The front flank downdraft is going to be going like this, coming out the front of the storm, hence the front flank downdraft. The rear flank downdraft is going to be wrapping around the back of the storm. It's going to give an extra burst of rain. And so basically the main areas of rain associated with a classic supercell. This is an example of a classic supercell. The main areas of rain are going to be the rear flank downdraft and the front flank downdraft. Both of them bringing rain and moisture down. Rain, cooled air along with that. So what's going to happen after this is just to make sure you know the inflow is what this updraft is feeding off of. The inflow is going to come out of the front of the storm, front flank of the storm, and that's going to be warm, moist air. We got this coming into the updraft, and then once it comes into the updraft, it comes down. All right. And so if this updraft starts to lower down, this rotating column of air starts to lower down, this is what I drew in before, that is called a wall cloud. And a wall cloud is one of the first signs that shows you that there may be a tornado associated with the supercell. And if this wall cloud lowers a funnel of rotating air and it comes up from the ground too, we get ourselves a tornado. And later into this video, we'll get into how that tornado is actually going to form. But I hope you understood how a supercell helps to generate a tornado in this case, and why supercells are so unique. So I stated before from MedOffice of the UK that the supercell is going to split into a right mover and a left mover. And in the northern hemisphere, the right mover will continue to strengthen. This right mover will develop a strong updraft and a well-defined rear-flank downdraft and a front-flank downdraft. And a hook echo is going to become clear on radar. So I've already explained the RFD and the FFD on the whiteboard. But over here, now I'm going to be explaining the supercell splitting. So this image is from the Austin Man. The title is Radar Animation of Haskell County Supercell on May 3rd to 4th, 2003. It was produced on the 20th of December in 2021. It's from Wikimedia Commons, and it is licensed on Creative Commons by 4.0. So here we're in Texas over here, and we have the thunderstorm forming. This image is of radar reflectivity, which is showing how intense precipitation is. So right now we just have a small thunderstorm, nothing major yet. What's going to happen? Oh, just watch. It's going to intensify. And now you see it's starting to develop these two sort of separate cells. And here it becomes much more defined. So now over here we're going to see two different cells. All right, we're going to continue to see them split. So now we see two different thunderstorms clearly now. So this one is going to be the right mover. The southern one is going to be the right mover. The northern one is going to be the left mover. That's how it's going to be in the northern hemisphere. So the right mover is going to be rotating with the Coriolis force. It's going to be rotating cyclonically, counterclockwise. The left mover is not going to be rotating counterclockwise. It's going to be rotating anticyclonically, which is clockwise. Because of that, the right mover is going to dominate because it has the Coriolis force and Coriolis effect on its side. So you see they're still splitting, they're further splitting, but they're still holding onto their intensity currently. We can see the left mover is starting to somewhat fizzle out, and the right mover is starting to gain traction. And this right mover is clearly getting stronger, stronger, stronger. And now this is what I want to show you here. So if you look at this, you can see somewhat of it's a straight line from where it says Haskell to about the boundary between Haskell County and Stonewall County. And it starts to curve slightly southward. And we can see it becomes more evident, this curve in the storm, as we get further into frames. And this is called the hook echo. This is apparent on radar. So really what this is just the storm wrapping around precipitation because of its rotation. And I have a better image of this. So this image is from the Storm Prediction Center. Its title is Tornado Classic Supercell Radar. It's on Wikimedia Commons. It was created on the 3rd of May, 1999. And it's licensed under public domain. So here we can clearly see this is from a strong supercell in Oklahoma. And we can clearly see this curvature from Midwest City to OKC down to Newcastle. We can clearly see a big curve in the storm. That's called the hook echo. It's also labeled here on this diagram. And this hook echo shows that there is strong rotation within this. It's one of the biggest signs of a tornado, like from a thunderstorm. So what this hook echo tells us is that the supercell is becoming mature and it's become ready for tornadogenesis. We can see the RFD wraps around this hook echo. So the rear flank downdraft that I was showing you previously on the whiteboard is at the back of this hook echo. All of this precipitation, all this big blob of precipitation, is back in the storm, and that forward flank gust front is labeled on the boundary. So right along the southern boundary of the storm before it starts curving into the hook echo. All right. So keeping our previous model of a supercell right here in mind, and this one. So when tornadogenesis begins, the rear flank downdraft is going to surge out of the storm, and the cyclonic and anticyclonic pairs of vortices will form, according to Orff et al. The RFD is going to help focus rotation near the surface on the cyclonic vortex, which will connect the rotating mesocyclone and form a tornado, which is from metoffice.gov.uk. And the exact science behind tornadogenesis is still not clear to us, but this is the best idea that we have. Alright, so now I'm going to be giving a few images based off of the research of Orff et al. So remember, this is our model of the hook echo supercell from previously. This mature hook echo clearly means that like the tornado is quite strong by now, but we're gonna slow it down a bit. We're gonna bring it back to when tornadogenesis is about to occur. So we're still gonna have our front flank downdraft, and the front flank downdraft boundary is gonna be something like this over here. And this is just the rest of the storm, not drawn to scale. So our forward flank downdraft boundary is gonna be coming down, and our rear flank downdraft boundary is gonna be coming down too. And where they both meet, basically like a southern corner of the storm, it's going to be a zone of convergence where winds are coming together. And where these winds are coming together, that around there is going to be the potential site of a tornado. All right, so after this, we're going to have the gust front, the rear flank downdraft boundary gust front is going to surge out. So what this is going to do is it's going to form pairs of rotation. All right. So what we're going to have is that we have our front flank downdraft boundary, and our rear flank downdrafts coming surging out. Our FD surge. And now this is the boundary. This is the gust front. This front flank downdraft boundary is still there. Our FDB still there. What's going to happen now is we're going to have this there is rotating like this. Right? That is the cyclonic rotation, not anticyclonic, counterclockwise rotation. So this vortice is going to be rotating counterclockwise. And there's going to be another vortice pair, right, this way. It's going to be rotating clockwise. So as I said previously, the cyclonic vortice is going to be favored. In this case, it's this vortice right here, because it's rotating counterclockwise. And there, over there, is going to be the exact location. Well, not exact, but very likely that is going to be the location of the tornado. Right in here, where the FFDB and the RFD, so FFDB, we get the RFD surge, we get the other pair, etc. And this is going to be the area, this FFDB. This is not the one surging out. The RFD is wrapping around, surging out. As I said previously, it's helping focus that rotation right there. And from this diagram over here, I'll try my best to show it to you. But over here, you see the downdraft coming down to where the location of the tornado is over here. That location of the tornado is going to be that boundary between the FFDB and the RFDB. And the RFD is wrapping around. It's helping focus that rotation right underneath the mesocyclone. And so the magic that's going to have to happen here is we get our wall cloud, our storm is whatever over here. The RFD is going to wrap around. It's going to form this rotation that we were talking about over here. And we already have this rotating mesocyclone. And it's going to help focus rotation. So we're going to get a funnel cloud up here. We're going to have surface rotation over here. And when this connects, if and when this connects, then we are going to have a tornado. And tornadogenesis will be complete. Once the tornado forms, the parent updraft is going to feed off the streamwise vorticity current, which has cyclonic and anticyclonic vorticity patches. The SVC is going to be focused around the forward flank downdraft boundary. The higher the buoyancy gradient along the FFDB, the stronger the SVC will be. Hence, the updraft will strengthen, meaning that the tornado will intensify. The tornado really starts to get going when the vertical vorticity sheet that provides the SVC with vorticity will become more active, which usually happens after tornadogenesis. The tornado also becomes more upright and aligned with the updraft so that it can take advantage of the SVC. Alright, so let's break this down. Keeping in mind our diagram from before and our radar image from before, I've constructed another diagram of a supercell, this time pointing out the rotational features. So first of all, I stated the streamwise vorticity current. So first of all, the streamwise vorticity current is fed by the vertical vorticity sheet. So because of all this wind shear that we have in the atmosphere that we were talking about previously, we have all of these vorticity patches. Vorticity in the atmosphere is just like an area of rotation. We have all of these vorticity patches, whether they're cyclonic or anticyclonic. The majority are going to be cyclonic because we're in the northern hemisphere. So all of these are just there, but when this supercell starts to take control of them, starts to feed off of them, then we call this the streamwise vorticity current. So the air from this is going to move, as this arrow is depicting, into the central updraft. The updraft is going to feed off of it. And this image where the tornado's down here, this is during this mature stage of the tornado, but before the tornado even forms, before we even have this tornado, we have the SVC. The SVC is already there. And just to tell you about, I was talking about the FFDB, the temperature buoyancy gradient. So we have our storm here. We have rain-cooled air in the storm. And the front flank downdraft boundary is the boundary between that rain-cooled air and that warm, moist inflow air that the supercell is feeding off of. The warm, moist inflow air also contains the vertical vorticity sheet. And so this warm, moist air and the rain-cooled air, the bigger the difference between this, the bigger the difference between these two air masses, the stronger the SVC is going to be. So as we were talking about the SVC is going to be located on the forward flank, and before the tornado even forms, it's going to be ingested into the updraft repeatedly, each vortex after vortex. But at one point, we're going to have these vortices, they start to combine. So these three start to combine, right? And they start feeding off of these. So they start to combine. So then we get one bigger vortice, which will be our future tornado. So we know that this isn't connected to updraft yet, but we have a vortice that is connected to the surface. And as we said, the RFD is going to help to focus both of these. And when they both connect, then that's where we get our tornado. And SVC isn't going to go away. It's still going to be there. The updraft's going to be feeding off of it. And so after this, our tornado is going to be better aligned. You can see it's aligned with the updraft to take advantage of the SVC. And once it starts taking advantage of the SVC and the vertical vorticity sheet starts increasing activity, this is when our tornado is going to start to increase in intensity. And once this tornado starts to get going, that's when the damaging effects of the tornado will become more prevalent as the wind speed starts to pick up. 0 STM, and the title of it is 2016-05-16 tornado north of Solomon, Kansas. It was taken on the 25th of May of 2016, and it is Creative Commons by 4.0. So what I like about this image is that you can see the entire supercell up here, and you can see the lowering of the wall cloud right here, and you can see a separate distinct tornado right here, and you can see how the precipitation is separated from it. Whether this be the RFD or the FFD, it's separated, which shows that the tornado is still in its early stages. So what this means is that a tornado in its early stages is not rain wrapped. So as we can see here in this time lapse of the tornado, which is by running on brains, it's called Tornado Time Lapse. It's from the 19th of June 2018, and it's Creative Commons by 4.0. We can see how the funnel cloud forms and then it connects. It almost seems like elephant's trunk, and it becomes a very well-defined funnel cloud. So after a tornado, it becomes aligned with the updraft. Its vortex structure goes from single celled to multiple celled if it already isn't, and it develops a central downdraft between these cells, whether it be 2 or more cells. The condensation funnel will become more evident, as seen right here. And towards the later stages in the tornado's life, vortex breakdown will become evident above 2 kilometers 2 kilometers AGL. What this means is that you'll have that multiple vortex set up at the surface, but as you get further up, that updraft is starting to weaken, which means that we're getting into the later stages of the tornado's life. And the vortices will become more disorganized as we go on, and this is the first sign of the tornado weakening. And after this, the tornado will start to become rain wrapped. So we can continue into this time lapse, and we can see that the tornado starts to become quite disorganized because the shape of it is so elongated. So this is a sign that it's starting to break down. And over here, if we go to this image right here, this is of the Joplin, Missouri tornado. It's by NWS Springfield. The title is Joplin Tornado Photo. It was taken on the 22nd of May in 2011, and it is public domain. This is towards the later stages in the Joplin tornado's life because we can see that it's completely rain wrapped. Both the condensation funnels well defined, and we can see, especially over here, that this is rain wrapped. This means that the tornado is getting into its later stages as the rear flank downdraft is wrapping around it and bringing precipitation. The infamous El Reno tornado was a very good example of a multiple vortex tornado. This is towards the beginning of the tornado, and towards the beginning of the tornado, there were multiple vortices, 1, 2, right there, and another one is going to form right here, a horizontal vortex. Very striking horizontal vortex right there. Another vortex right there, another one right there. And they're all, if you notice, they're all rotating around one central downdraft, as I said before. And this tornado was so violent that even in its early stages, it had multiple vortices. This is already at least 3 vortices. Later, one became evident, clearly at least one. This looks like another one over there as it started to form. And the tornado later became well defined and it started to become rain wrapped as well, as you can see. This is starting to become rain wrapped. And here clearly by this point, the tornado is definitely completely rain wrapped by this point. And this tornado was 2.6 miles wide according to weather.com. So this tornado was a massive rain wrapped tornado, even bigger than the Joplin one. And we can clearly see here that even within this rain wrapped structure, we know that vortex breakdown is going to be occurring up towards the top. I'll explain that later on the whiteboard. what we can see over here, right here, we can see even though this is completely rain wrapped, we can still pick out the multiple vortices. So we know that it's still later in this tornado's life, but we know that still below 2 kilometers up in the atmosphere, we still have that multiple vortex set up. So we can see that right there. And the tornado is completely rain wrapped, meaning that it is going to weaken, as I have stated multiple times. This video of the El Reno tornado that I just showed you was from Ray Bohack. Its title is May 31st El Reno EF5 Extended Version. It was on Wikimedia Commons. It was uploaded there on the 10th of June in 2013. And it is licensed as Creative Commons by 3.0. So as I said previously, this is most likely the best example, not very visible, but the best example of the multiple vortex nature of this tornado. You can see one vortex there, another very obscure one over here. So this shows that even during the vortex breakdown stages where the tornado is rain wrapped, as I said again, the multiple vortice structure is still there. And this is what makes rain wrapped tornadoes so dangerous. We can't even see what's in them. We don't even see them coming. And they can bring so much destruction with them. Alright, so as I stated before, the tornado is going to be going as it matures from a single-celled vortex to a multiple-celled vortex. So in general, in the beginning it's now a single-celled vortex. In the single-celled vortex, what's happening is at the surface, the inflow is just coming in and going straight up as an updraft. It's just going straight up through the updraft, right? So that's only during its not during the mature stages. Before that, during the early stages of the tornado, and later, when it becomes more mature, it's going to become at least two-celled, or it may become multiple-celled. So the idea behind the two-celled tornado vortex applies to all multiple-celled tornadoes, but you just need to know that a tornado does not have to be limited to two cells. As we saw in the video of the El Reno tornado, there were multiple vortices in that. So the idea is here that we have this one central downdraft over here. The air is just coming down that one central downdraft, and then it's going back up, combined with additional surface inflows going back up. So we have this area where it's rising, this area where it's rising, and we have the central downdraft over here. So the areas where it's rising can be as many vortices as you want, but there's always going to be one central downdraft. So that's the main difference. In the singular cell, there's no central downdraft, and in a multiple cell, there is multiple downdrafts. And this central downdraft is a big sign that the tornado is becoming much more mature, and it may become more damaging. And now, once it becomes multiple celled, and towards later stages in its life, it'll become rain wrapped, as we saw in the picture of the Joplin tornado. And also vortex breakdown will become evident above 2 kilometers. So what that means is we have our updraft, right? Just like we have over here. And it's going strong, but as soon as we hit like around 2 kilometers above ground level, then it starts to do all kinds of funky stuff. It doesn't say is that like well-defined single cell or multiple cell. This starts to become multiple vortices. They're all wrapping around each other. And that's a big sign that the tornado is starting to weaken. It's not going to actually weaken until it actually lifts off the ground. As long as it's on the ground, it's a tornado. But once it starts decomposing from upper levels, then sooner or later it's going to start decomposing from the bottom layers. So now what's going to happen after vortex breakdown occurs above 2 kilometers AGL? What's going to happen is that the SBC is going to start weakening. And the reason the SBC is weakening is because BBS activity will decrease along the forward flank downdraft boundary. Because that rain cooled air, I'll bring back the diagram we had before of the supercell with the hook echo. That rain cooled air that we had in here, and that's not how you spell cool, but you get the idea. The rain cooled air we have up there, and the warm inflow that we have here, the difference between these two air masses is decreasing. The difference between them is decreasing, leading to less of a less of a gradient between them. And the reason they're decreasing is because the storm itself is starting to weaken somewhat. And that because that gradient is lower, the buoyancy gradient is lower, the VBS will become less active. And because the VBS is less active, the SVC will become weaker, meaning the updraft will also be weaker, meaning the tornado is also going to start to decompose. Now, what really brings the tornado to its death is what happens is that the cold pool outflow is going to start overtaking it. So now everything since the last citation I had, everything up into this video has been from Orfadal. So now what's going to happen is that we have our cold pool. The cold pool is the rain cool air that the RFD is bringing back from that thunderstorm. So cold pool is out here, right? Again, this is not the scale at all. If our tornado is over here, what's going to happen is that this RFD has already started to wrap around the vortex because the rain wrapped vortex is evidence of that. What's going to happen is at the surface now. At the surface is where it's going to start creeping in. And the key is when it starts creeping at the surface, it's going to cut off this warm air. It's going to cut off this warm air inflow. No matter how much warm air there is, it's going to be cut off because at the surface there's going to be cold air. So now cold air is going to cut off that warm air just at the surface. So when both around the tornado the downdraft is wrapping, and at the surface the downdraft is the cold pool is bringing in cold air at the surface, what's going to happen is that the tornado is going to start developing kinks in the structure, and after this those kinks will become visible in the condensation funnel, and the tornado will rapidly start to roll out. This is from Met Office Cycle of the UK. The rear frank downdraft is going to circle down and cut off the tornado's vortex, along with the cold pool at the surface, and this sometimes is associated with a quick burst of rain. Finally, the cold pool at the surface will completely overtake the vortex at the surface, and the SVC will break down, and finally the tornado will be gone. So what's going to happen is that the cold pool air from over here, cold pool, right? So first we have our RFD. Our RFD is going to start to, you remember how it helped focus the energy here? Well, now it's going to start wrapping around this. First it's going to become rain wrap, and then it's going to start wrapping around it to the point where it starts again. But remember, the tornado is still a tornado. Even this updraft is starting to break down up here. And even if the RFD is starting to weaken it, it's still a tornado as long as it's in contact with the ground. So what's going to happen here is that as the cold pool creeps in, the SVC is going to weaken because the gradient is reducing. So all these vortices, a lot of these vortices are going to go away. And along with that, the tornado is going to have to start to lift because of this cold air. What's going to happen is that there's going to be vortex breakdown at the surface now too. The two-celled structure is going to start to lift. It's going to lift, and we're just going to be left with the funnel cloud, which then retreats back into the mesocyclone. So once the cold pool overtakes the surface vortex, that's the point of no return. The tornado will have dissipated by then. And it's very visible when a tornado is dissipating. It turns into from its like strong or straight appearance, say like that, it becomes very like rope-like. Hence why the turn is roping out. We'll see that in a video later. So throughout the video, when I was explaining things on the whiteboard, most of it came from the Orfadal document, which I've completely cited over here. And I did not get information to use the images out of it until today. So that's why this is towards the end of the video and not exactly where I was explaining the stuff, but I hope this still gives you a better understanding of what I was trying to show on the whiteboard. So this image is figure 5. This is showing the convergence of the winds and with the arrows. It's also showing the potential temperature perturbation. Basically, you could understand it as the temperature gradients within the storm. And I was talking about where the RFD and the FFD like the rear flank downdraft, front flank downdraft, where they are intersecting, that's where you have the higher amount of convergence. That's where the tornado or the rotation would form. So you can see that clearly right over there, where the RFD boundary and the front link down to the boundary are intersecting. You can see all the arrows are pointing towards here, meaning that's where the air is converging. And this image expands upon that. This is figure 6. A through C are the same exact image, just advanced in time. So here you can start to see that bulge coming out that I was talking about on the whiteboard. Here you can clearly see that coming out, the bulge of with the RFD surging out. You can see the rotation starting to begin. And over here is where you can see it the best. So you can see how the RFD has been surging in towards here. And you can see the anticyclonic part of the rotation, the cyclonic part. The cyclonic part is much better defined here clearly. And this green box is this image. This is a zoomed in image of this area in this green box. And this shows the winds within the storm. And the red contours are areas of rotation. And clearly you can see that this is the beginnings of the SVC that you can see right here, all these patches of rotation. And this area right here is where the tornado is very likely to form. And over here on this image, you can see exactly how the SVC is going to be structured. So this area is the vertical vorticity sheet, and the SVC is being advected up into this updraft. So you can see all these patches of rotation. This is the main updraft over here. And this one right here, this red, the red arrow, the vortex that's pointing to, that's the strongest of the SVC, which will end up merging with the updraft to form the tornado. And this is when the tornadoes mature, this image. And this, you can see this, the tornado is probably down here, but you can see the tornado extending into the updraft, because this is from 0 to 9 kilometers. And you can see how the SVC is coming off of the surface, or surface inflow, and just advecting into this updraft. It's a really nice visualization of how this is happening. This is, all these colors are streamwise vorticity, which is basically rotation, a measure of rotation. And this shows once the tornado is very mature, you can see how straight the updraft is, how well aligned it is. So these show how the air that's in the SVC is advecting around this updraft. You can see how it advects and feeds into this updraft with all these vortices surrounding it. This video right here gives a really nice visualization of the SVC in tornadogenesis. So you can see, I'd like to pause it here. So this is the SVC. You can clearly see all these patches. Red is cyclonic vorticity, blue is anticyclonic vorticity. This is looking from the west. So this is the hook echo is wrapping around over here. And as I showed you, that outward bulge, you can, I don't know how well you can see it, but this is the outward bulge. This is the anticyclonic part. This is the cyclonic part. And you can see how the cyclonic part, over time, it gains much more strength than the anticyclonic. The anticyclonic part just starts to fade away pretty much. The cyclonic part starts, you can see how it's ingesting all of these vorticity currents and how it becomes a tornado from that just initial vortex. And the final thing I have to show is a visualization of how the air is moving in SVC. And also this image also shows vortex breakdown. You can't see it very well on this one, but over here you can see how this is just a round base, and further up you see how it's just breaking apart into multiple different vortices. And it's just overall wider, as you can see. So that shows the vortex breakdown towards the top, as this is in a much more mature stage. And this is how the SVC is advecting into the updraft as a whole. So again, all of these have been used with permission from the American Meteorological Society. All of this was under copyright. This is used under permission, and it's from the Lee I. Orff article, Evolution of a Long-Tracked Violent Tornado Within a Simulated Supercell. And I hope this helped you visualize even better what I was showing on the whiteboards. And just as a side note, all of this was supercomputer generated. It was generated by the Blue Water supercomputer using Cloud Model 1. End of the video conclusion. So this image is by Jason Weingart. It's called The Evolution of a Tornado. It's taken on the 24th of May 2016, and it is CC by 4.0. And so this image is really nice because it's a photo montage of, I believe it's 8 different shots, and it shows the tornadoes at multiple stages. There are 7 different stages of the tornado that we can see visibly. So here is before it's even touched down. It hasn't touched down yet, but we can see clearly there is some sort of a funnel. Actually, no, it has touched down. If you look right here, you can see some dust rising. But this is very early stages of the tornado. This one too is also the very early stages. We can see it's in contact with the ground. It gets a little bit weakened. We can see these kinks in the thing, and then it's regaining strength. It becomes well oriented with updraft. I compare the orientation of this to this. It's much better oriented with updraft. Becomes stronger, and even towards here, now we can even see that it's starting to become rain wrapped. So this clearly shows the evolution of a tornado's lifespan of it. It doesn't show the later stages, but this video will. Again, we already watched part of this, but this is running on rains. It's called Tornado Time Lapse. It's from June 19th, 2018, and Creative Commons by 4.0 from Wikimedia Commons. So we can see this is the beginning of funnel cloud. You can see it touches down, the condensation zone starts to become better defined. Now we can see the tornado starting to become mature, but it is starting to become slightly elongated. So we can see it's starting to retreat, starting to have some kinks in the structure, clearly weakening, a lot of kinks, very thin, starting to clearly, this is the definition of a tornado roping out. This is a very good example of a tornado roping out. And now it completely dissipates now. You can see it's all gone. So that, in about 36 seconds, is the lifespan of a tornado. So for this video, the sources of Orf et al. And medoffice.gov, the UK, were extremely helpful. And I believe every image and video on this was from Wikimedia Commons, so they were very helpful. And I hope you understood the lifespan of a tornado and the complex processes involved behind the formation of a tornado and the ending of a tornado. Thank you.